The boundary between a static museum display and a flight-rated aircraft is defined by verifiable structural compliance, not by visual completeness. When an airframe suffers severe physical trauma, returning it to the sky requires inspectors and mechanics to prove that each repaired or newly fabricated load path meets approved dimensions, materials, and workmanship. If that proof cannot be established, the aircraft ceases to be a flight-rated machine and remains a static collection of parts. This is the baseline constraint for the heavy bomber now known as Champaign Lady. Originally accepted into the military inventory in 1945, this B-17G Flying Fortress was built by Lockheed Vega and assigned the serial number 4485813. Delivered too late to see combat in the Second World War, the aircraft transitioned through decades of specialized commercial operations. Its operational life ended in 1980. Operating as a civilian firebomber, the aircraft was involved in a reported takeoff accident at Bear Pen, North Carolina, although surviving secondary accounts do not all describe the sequence in exactly the same way. The bomber came to rest in the surrounding terrain. The flight crew survived the impact, but the physical airframe suffered catastrophic trauma. The mechanical forces of the crash were followed by a severe post-crash fire. This localized fire established a permanent engineering boundary for the wreckage. The flames burned the forward fuselage beyond useful flight-rated recovery. When a heavy aircraft burns on the ground, the thermal damage can extend far beyond the visibly melted zones, and every nearby structural member has to be evaluated instead of trusted by appearance. For serial number 44-85813, the fire destroyed the usable forward body and forced later restorers to separate condemned material from components that could still be tested, documented, and rebuilt. The aircraft was no longer a cohesive machine ready to transfer aerodynamic loads. It was a fragmented wreckage site exposed to the elements. Over the following decades, the surviving material moved into a larger composite restoration effort after the Schiffer family acquired remains from multiple B-17 airframes. Today, the project is managed by the Champaign Aviation Museum in Ohio, with serial number 44-85813 preserved through selected original structures and documented identity, while other major sections come from donor aircraft or new fabrication. The museum's objective was operational, not cosmetic. The rebuilt bomber had to be restored toward flight, not arranged as a quiet, static display. The baseline condition of the wreckage dictated the next engineering demand: a continuous, load-bearing centerline capable of carrying tailwheel impacts, aerodynamic torsion, and repaired joint loads through one verified path. The museum held the registered identity and selected surviving structure, but it still lacked the forward geometry needed to connect the cockpit area, restore the nose profile, and tie the rebuilt wing and engine structures into that path. The missing forward section therefore became an inspection boundary, not a cosmetic absence. Restorers had to determine where fire damage ended, retain only viable metal that could be tested and documented, and regenerate the remaining structure through approved repair or fabrication. Before physical assembly could safely begin, the museum team had to answer a more specific procedural question. How could a verified centerline be rebuilt from an aircraft whose nose history had already been broken once before Bear Pen? The geometry of a heavy bomber relies on a strict center of gravity, a precise aerodynamic balance point that dictates how the flight deck, engines, tanks, and structure must work together. Long before its civilian firebombing career, this specific B-17 underwent a radical physical alteration into the Boeing Model 299Z testbed. Available restoration histories describe the aircraft as being used in the Curtiss Dash, Wright and Boeing test program to evaluate the massive XT-35 turboprop and the J-65 jet engines in a controlled airborne environment. To test these heavy propulsion systems, engineers mounted the experimental units directly into the extreme forward nose of the bomber. This unique modification transformed the aircraft into a 5-engine machine. The sheer physical mass of a large prototype engine bolted to the front frame pushed the aircraft outside its safe balance envelope. To counter the nose weight, the engineering team removed military armament and shifted the cockpit aft by several feet, though the exact 47-inch figure is not consistently confirmed in accessible sources. The offset made the testbed controllable. but it also meant the standard B-17 nose had already been structurally displaced before the later civilian conversion. When the military and manufacturer testing programs concluded, the specialized airframe transitioned into the civilian sector through a sequence of owners. Ewing Aviation acquired the modified bomber in 1966, and the aircraft later moved through the Ewing Kolb and Arnold Kolb operating history before Black Hills Aviation became associated with its firefighting career. Mechanics then initiated a complex conversion into an aerial firefighter. To restore the standard aerodynamic profile necessary for stable low-altitude flying, mechanics retrofitted a standard forward fuselage harvested from a completely different airframe. They also installed heavy internal retardant delivery tanks, described in restoration accounts as 2 tanks reported at 1,200 gallons each. This new configuration restored the familiar aerodynamic lines of the heavy bomber, while repurposing its internal payload bays for dense liquid drops over forest fires. In 1980, that specialized heavy configuration failed at Bear Pen during takeoff. The impact imposed severe deceleration loads, crumpled the replacement nose section, and collapsed the forward wing roots. The flight crew escaped, but a localized post-crash fire then ignited around the forward structure. Under the fire damage rule already established by the wreck, Bear Pen became the aircraft's second loss of a usable forward structure. The replacement nose was condemned, while selected components outside the worst burn zone, including reported inboard wing and center truss structure from serial number 44-85813, could be retained only after inspection and rebuild. Selecting the correct load-bearing structures became a mapping problem. Restoration reporting identifies selected inboard wing and center truss structure from serial number 44-85813, fuselage sections from donor bombers, a donor vertical stabilizer, and newly fabricated nose and radio room structure. Investigators had to assign each viable component to one restored airframe without pretending all of the metal came from one wreck. This introduced the procedural challenge of airframe amalgamation. In aviation reconstruction, combining multiple aircraft into a single flying machine requires a clear distinction between historical identity, registration records, maintenance documentation, and structural airworthiness. The FAA registry lists N3154S as a B-17G with serial number 44-85813. But that registration does not by itself make every donor section automatically acceptable for flight. Each incoming structure had to be documented, inspected, and treated as a traceable repair or replacement component within the restored aircraft, not as anonymous salvage. Sourcing parts from at least 4 separate airframes created an immense geometry problem. While wartime factories built thousands of heavy bombers, the manufacturing tolerances of the 1940s meant that no 2 fuselage sections were perfectly identical. Rivet hole patterns, bulkhead flanges, and stringer alignments varied slightly from one production run to the next. When engineers attempt to mate the forward section of one donor to the mid-body of another, the structural load paths do not automatically align. To move from documentation into geometry, the engineering team established a rigid datum line through the restoration space. Salvaged components were supported in fixtures measured against that reference and corrected before permanent attachment so misaligned donor bulkheads could not create stress concentrations or mandatory reworks. The physical integration of foreign components began in isolation. When a donor wreck arrived, investigators drilled out original rivets, extracted only undamaged stringers and formers, discarded compromised surrounding metal, and kept the recovered pieces segregated until cleaning, corrosion treatment, and non-destructive testing verified that they had not suffered heat fatigue, crash deformation, or severe intergranular corrosion. The original design of the heavy bomber relies on a semi-monocoque structure. This means the external aluminum skin carries a significant portion of the aerodynamic flight loads, working in tandem with the internal skeleton. Because the skin itself is a structural element, the joints between donor sections and the primary airframe required more than surface alignment. Every transition had to be custom fitted with precise splice plates, allowing dynamic tension and compression forces to transfer smoothly across the invisible boundaries where one donor aircraft ended and another began. With the donor integration logic defined, the project still had to retrieve the remaining viable skeleton of 85-813. A narrow window of several years separated the structural loss from the initial extraction of viable parts. In the mid-1980s, the physical remains of the heavy bomber were targeted for recovery, with some accounts placing Tom Riley's acquisition in 1985 and others describing the transfer more broadly. The operational objective was not to rebuild this specific airframe at that time. Instead, the salvage effort focused on harvesting specific structural components to support a separate bomber restoration project. This extraction was a selective harvest, not a full aircraft recovery. The goal was to identify viable subassemblies, document their condition, and remove useful structure for another restoration, while the surviving accounts leave the exact field equipment, soil conditions, and hand-carrying sequence unresolved. The surviving aft tail sections and safely recovered structural pieces were then manually loaded onto flatbed trailers and hauled away from the humid, corrosive forest environment. After the necessary components were harvested for the external project, the remaining skeleton of the bomber was placed into static storage. It was a collection of stripped parts consisting primarily of the aft fuselage and the registered identity anchor, stripped of its most valuable internal frames. The wreckage sat dormant, shielded from the elements but structurally stagnant. Roughly 2 decades later, in 2005, the Schiffer family purchased the surviving, heavily stripped structural assemblies to begin a ground-up restoration in Ohio, forcing a complex physical relocation of fragile components. Road transport introduced a new handling hazard. Without the stabilizing relationship of skin, stringers, bulkheads, and longerons, the stripped frames had to be supported so vibration and vertical shock would not crush aged aluminum. Once the loads were spread safely, flatbed trucks carried the remaining wreckage to Grimes Field in Urbana, Ohio. Upon arrival at the museum hangar, the new engineering team initiated a comprehensive physical inventory. They had to assess exactly what remained of the aircraft after the original crash, the subsequent fire, and the original selective harvest. Every surviving stringer and bulkhead was cataloged, checked for transport damage, and mapped against the empty spaces in the airframe. This baseline assessment confirmed that the primary load-bearing engine mounts were missing. The salvaged skeleton provided a foundation, but the nacelle and engine mount structures had to be created through a separate manufacturing effort that would ultimately absorb more than 14,000 hours of labor. Serial amalgamation had secured primary structural bulkheads for the fuselage centerline, but it could not supply the complex engine nacelles. Because these structures house the main landing gear and support the heavy radial engines, suitable donor units could not simply be harvested and installed. The team therefore pivoted to scratch building 4 independent engine nacelles from raw aluminum stock, activating the complex process of blueprint fabrication. The volunteer team acquired original 1940s Boeing archival drawings, including records preserved on microfilm, and later converted into usable reference material. Those documents gave the dimensions, but not the factory tooling that once controlled bulkhead spacing, skin curvature, and attachment geometry. Volunteers, therefore, had to interpret the drawings, compare the printed data, and reverse engineer new fixtures and form blocks before any flight-rated parts could be made. The geometry demands of an engine nacelle are completely unforgiving because the nacelle is a load-bearing node, not a simple fairing. Its internal skeleton must absorb radial engine torque, transfer thrust into the main wing structure, and allow the lower inboard section to accept the vertical kinetic energy of the landing gear during touchdown. If the complex internal bulkheads are manufactured with even a fractional degree of misalignment, the engine thrust line will sit off-axis, generating dangerous asymmetrical forces during flight. To achieve the required mathematical precision, volunteer engineers utilized advanced trigonometry to calculate the exact outer curvature of every individual nacelle rib. Based on these mathematical coordinates, they machined heavy steel form blocks. Once the form blocks were ready, forming began. Flat sheets of raw, aviation-grade aluminum were clamped over the custom templates, mechanically pressed, and hand-formed against the calculated curves. Each finished part then had to meet the specified material condition, heat treatment requirements, dimensional limits, and inspection standards before it could be accepted into the assembly. Once the individual components passed quality inspection, they were locked into the scratch-built assembly jigs. Thousands of solid rivets were driven to join the external skins to the internal formers, slowly building the rigid three-dimensional nacelles from the bottom up. Restoration reporting from the nacelle fabrication period described more than 14,000 hours of labor invested in that work, while later updates reported the 4 nacelles and engine mounts rebuilt and ready for installation. Before that industrial momentum could settle in Ohio, primary leadership was suddenly removed. Around the time the first salvaged bomber parts were reaching Grimes Field, project founder Jerry Schiffer died in an unrelated aviation accident. The exact phrasing differs between accounts, with one describing his death just before the first shipment and another placing it on the day the first parts arrived. The surviving family and aviation community faced a stark choice: halt the incoming shipments, liquidate the bare structural frames, and dissolve the effort, or create a formal organization capable of carrying the restoration forward. They chose continuity. The restoration was organized under the Champaign Aviation Museum, converting a family-driven effort into a structured institutional project whose execution now depended on volunteers, documentation, quality control, and long-term public stewardship. A formal organization building a flight-rated aircraft requires rigid operational standards, transparent quality control, and strict regulatory oversight. The hangar floor was systematically configured into an active aerospace manufacturing facility. To meet the stringent requirements for a federal airworthy certificate, the project required a highly disciplined workforce, capable of interpreting complex technical data and performing aviation-grade metalwork. This necessity led to the assembly and training of a large volunteer manufacturing team, with earlier accounts describing nearly 90 active volunteers and later reporting noting that about 500 people have contributed to the project over time. On the hangar floor, that discipline became a sequence of controlled shop actions. When volunteers attach a new aluminum skin panel or integrate a new internal structural rib, fastener spacing, edge distances, and material thickness must match the original 1940s engineering data. The assembly process is deliberately slow and iterative. Each panel is clamped into position, pilot drilled, removed for edge deburring, treated with corrosion inhibitors, realigned with temporary sheet metal fasteners, and only then permanently secured with solid aviation rivets. If a single rivet is improperly driven or bucked, the designated inspector rejects the work. The flawed fastener must be carefully drilled out without enlarging the surrounding hole and completely replaced. Every structural milestone requires precise documentation. The technical logbooks had to demonstrate an unbroken chain of compliance, linking raw materials and installation methods to modern aviation safety standards. The engineering standard is absolute conformity to the factory blueprints. The scale of that commitment appears most clearly in labor time. Rebuilding a heavy, multi-engine bomber without an intact factory assembly line or original manufacturing jigs requires an immense, sustained expenditure of manual labor. Over the past 2 decades, the restoration has absorbed an estimated 370,000 volunteer hours. This immense metric represents the combined effort of converting damaged wreckage, donor assemblies, and archival manufacturing data into a continuous structural center line. The aircraft known as Champaign Lady now sits in a state of advanced physical assembly. The primary fuselage sections, the complex tail group, and many critical flight control surfaces have been rebuilt or are nearing completion, locked together into a coherent aerodynamic shape. Major wing integration and systems work still remain before the aircraft can move from restoration floor to active flight line. The remaining operational question is whether final assembly, inspection, and certification will validate that geometry for return to the active flight line.